Hi, I'm Ike Ellis, and we're going to look at data modeling trends for analytics. Specifically, we'll look at how we can create a modern data lake that will support Power BI in a cost-effective, high-performing manner that's easy to maintain and change. A little bit about me. I am the general manager for the data and AI practice at Soliance. I'm also a Microsoft MVP. I speak at conferences, I write books, I am readily available on Twitter if you need to talk to me. I like making new friends, and hopefully we'll get to know each other a little bit better. We're going to talk about traditional enterprise data architectures. We'll look at their problems and weaknesses, and then we'll look at how a data lake can address those things and how we can properly organize a data lake for use with Power BI. So we build enterprise data architectures or analytical systems for all kinds of reasons. We might do it for fraud detection. We might do it for decision support. We might do it because we need tactical reporting. We might be creating an advanced analytic platform for machine learning or maybe for deep learning. We might create historical data places where we can archive data cheaply and affordably and get it off of our transactional systems. Traditionally, what we've done for like the last 2 or 3 decades is we've pulled data from multiple data sources, like a financial system or an accounting system or a warehouse or inventory management or something like that. We've brought it into staging. Staging is only there so that if we have a problem with moving data in reporting, we don't have to add additional load to the source systems again. So we use staging to decouple our data pipeline process from the source, right? Then from staging, we'll go to the ODS, or Operational Data Store. An Operational Data Store is a place where we gather the data for permanent storage from all the different source systems so that we can join them together. So if you've got 100 tables in an inventory management system and 50 tables in your financial system, you're going to have 150 tables in the ODS, but they'll be available to join together if you'd like that for analytics. And then we will, from there, move the data into a star schema in a data warehouse or a data mart. A star schema, if you had 150 tables in the ODS, maybe you only have like 12 tables in the data mart. It's flattened, it's highly filtered, it's clean, it's organized and prepared. There's heavy data modification when you get into a data warehouse. And then once it's there, you might build analysis services cubes from that, or you might build a Power BI data model from that. Those are all available to you. So star schemas, which are what we use in a data warehouse or a data mart, they're just tables that are organized very simply. Typically, the tables are either a fact table or a dimension table. Fact tables are numbers. They're like sale amount, or number of employees you have, or number of inventory items you have on hand, or number of RVs you sold, right? Whatever you're doing. So fact tables are numbers. They also have foreign keys. Those foreign keys relate to primary keys in dimension tables. Dimension tables are the by numbers. So for instance, if you were looking at sales by region, the sales would be in the fact table and the region would be a dimension table. If you were looking at sales by employee name, the sales would be in the fact table and the employee dimension would have the employee name in it, right? So the reason why they're called star schemas is you have one central fact table and then you have these dimension tables around it branching out like a star. When you build fact tables, one of the most important decisions you can make is the grain. You really care about the level of detail you're putting in the rows. And the reason why that's important is if your decision makers want to see an individual sale, let's say you sell homes, and you sell maybe 5,000 homes a year, then you would want each individual home sale in the fact table. But if you're Walmart and you're selling millions of things every minute, you wouldn't want the individual transaction in your data warehouse. You would want to summarize the grain in the fact table. So you would say maybe total amount sold by hour, because maybe the hour is statistically interesting to the decision makers and the data scientists, and they track things by hour, and so you would sum it all up by hour, and that would be your lowest level grain. Choosing the grain appropriately will determine the size of the data warehouse, and it will determine how low you can drill into in the data in your reporting. So it's an important thing to identify the measures that you're going to be analyzing and identify the grain, and then create the fact table in the data warehouse appropriately. Now, the reason why we make star schemas are that they're easy to understand, we'll have one version of the truth. It's easy to create aggregations doing a single pass over the data. We get faster queries, and it's a good place to feed cubes if we need to, or feed Power BI. The reason why I'm being deliberate in telling you the importance of a star schema is I've heard a lot of industry noise out there from other vendors that say things like, you don't need to create a star schema because we have columnar indexing, or we have the super fast disk technology, or we do all sorts of analysis to say that you don't need a star schema anymore. You can have transactional tables like in the ODS, and you can just build analytics off of the transactional tables. And I'm telling you, if you do that, you'll regret it. What I always say is you can either start out by making a star schema, or you can one day wish you did. Those are the two choices. So star schemas are still important. Even in a data lake, star schemas are still important, and they're still valuable. Now, with this common enterprise data architecture, let's say you built this with SQL. So your source data might be SQL, staging is SQL, ODS is SQL, data warehouse is SQL. And you built this ETL tools. ETL stands for extract, transform, and load, moving the data from the left to the right all the way down the EDA. Let's say you built that. You probably had some weaknesses that you ran into. One weakness is, let's say that in a Power BI report, you want to add one column that your EDA doesn't have yet. Well, you identify that column in the source system, and then you have to change 9 different places you have to change in order to get that column into the Power BI report. And that took a long time. It was very fragile. You likely introduced some errors in your system, and you had a very hard time making changes to it. And so you probably avoided making changes to it. In fact, a lot of people in Power BI just started going to the source directly and extracting the data from the source into Power BI and avoiding the enterprise data architecture altogether because it was too cumbersome to maintain and too difficult to change. And so what that meant is that for all these different Power BI reports, you're just extracting data from the source over and over and over again. And you had a lot of different problems with this, right? These Power BI reports wouldn't be consistent with each other. So one report would say something vastly different than another report. If you needed to change something about the data model, you might have had to go into 5 different reports to make the change, and maybe you missed one, so 4 had a change and the 5th one didn't, and now they're inconsistent. There was a lot of overhead in maintaining all these different reports with all the different data sets and all the different extractions. And then you loaded the source system. The source system was suffering in performance because you're repeatedly getting the same data and cleaning it over and over again. And the data models, when people do this, tend to look very bad. They tend to have tons of tables in them and lots of logic and lots of DAX, and they're very slow to refresh and very difficult to maintain. So that's one weakness. Another weakness is that SQL Server being used for staging and ODS is not that great. There's a couple of reasons why it's not that great. The first reason is SQL Server was not designed to be a staging and ODS location. It has been used for that by many people, but it was not designed for that. SQL Server was designed to be a highly consistent storage system for transactional data. So if you were Dell.com and you were tracking your different orders, SQL Server is great for that because SQL Server can handle the massive consumption of data by thousands of people in a highly performant manner. But for ODS and staging, it's way overkill. It writes data multiple times. It does locking and blocking. It has indexing and all this stuff that isn't really necessary for those locations. All we really need is to load the data and leave it there for analytics. We don't need all that stuff. SQL is also expensive. It costs a lot. So when you use it for things like staging, you're spending all this money and you're not using all the horsepower necessary for it. So there's got to be a better alternative than SQL for these things. Another weakness of these systems is that these big, large data warehouses or data marts have been very difficult to maintain. ODSs can get very big, terabytes and terabytes of data, and they can be really difficult to maintain. It's hard to back them up. It's hard to restore them. It's hard to create a dev environment and a test environment and a staging environment. It's hard to use source control with them. It's hard to clean the PII, the personal identified information, out of them. Creating tests in these organizations are difficult because the databases are just so big that the tests just take so long to figure out if things are working or not. So people don't like to test these big, large things all the time. Another weakness is if you have a huge data warehouse and you're trying to move it into Azure, it's very expensive and cumbersome to do that. And here's why. When you use Azure or AWS, you're fundamentally getting charged for 4 different things: CPU, memory, disk, and network. And it doesn't matter how they bundle the pricing, whether they call them DTUs or they call them RUs or whatever they call the metric they're charging you for. Underneath that metric is CPU, network, disk, and memory. That's what's being charged to you. And of those things, CPU is by far the most expensive. CPU is very, very pricey. So when you have a great big data warehouse, you need a lot of memory. And in the cloud, memory is anchored to CPU, and CPU is really expensive. So let's say that you have a data warehouse with like 10 years of data in it. You and I both know that your decision makers are not using 10 years of data. They're probably only using the last like 14 months of data, really. But in this great big data warehouse, you have 10 years of data. It's massive, it's gigantic. And when you move that thing to the cloud and your decision makers say, hey, that thing's not fast enough, make it faster. You have this great big knob to turn to say, okay, that data warehouse, it used to cost me $5,000 a month, and now it's costing me $10,000 a month. And people notice bills that are that high. So what we'd rather do than have these great big ODSs, these great big staging databases, is we'd rather come up with much smaller, cheaper things. These small, cheap things are much easier to turn the knob to. If we have smaller dials, right? So instead of a great big ODS, if we have a lot of smaller files or something like that, if we go to make them faster, it's a small knob to make them faster. It's not a great big expensive knob to make it faster. So when you have a small data mart, rather than it costing, $500, it's costing $1,000 to make it twice as fast. And that's more affordable for the organization, and people might not be offended by that, right? Like they would if you want to change something that's 10 grand a month to 30 grand a month, right? Okay. There's another problem in that there's no separation of concerns in the architecture. So remember all those things that we use to create it in an EDA, they tried to make one EDA do all of those things. So for instance, this is a very bad alerting system for fraud detection, right? And the reason is there's a data latency problem. As you move data from source all the way to the cube, it just takes a long time. And when it takes a long time, people, they get upset. Partly it's our fault, right? We were using words like real-time data analytics. And there's nothing real time about something like this. To move data from the source all the way to the cube, it's going to take probably an hour, right? Maybe 4 hours, maybe all day. And then it's not going to take a minute, is my point, right? And it's just the action of ETLing all that data from one thing to the next thing to the next thing to the next thing. It just takes some time to do that right. So we have built data lakes that look like this. And we've been doing this for a few years now. Every data lake has a capture, a store, and a deliver. So a data lake is a file-based, not a SQL-based analytics system. And this is important. Let's talk about this for a second. If you have a relational store like an Oracle or SQL Server data store, and you move data into a file-based area, now you're building a data lake. And that's all it is. It's as simple as that. This is not complicated. So what you're doing is you're removing a relational database like SQL Server, and you're replacing it with files. That's it. So we have files in staging, files in ODS, and then we might still use SQL Server for our data marts, but our data marts will be much, much smaller than a great big giant data warehouse, right? So don't be afraid of files. We are not talking about CSVs or JSON files mostly in a data lake. We can store those in a data lake, but we don't have to. Instead, we're using a format called Parquet. Parquet is compressed. Parquet has reduced I/O. Parquet is splittable and scalable. So what is a Parquet file? It's a column store. If you've been doing SQL Server for any amount of time, you've been hearing a lot since 2012 about column store. Parquet is a columnar data storage method that's file-based that gives you strong data typing, meaning we have data types in there. So it's not like CSV where everything's a string or, there's all sorts of bad data in there. Parquet can preserve the data structure. It is compressed and it is fast, very, very, very fast. So we can switch from SQL Server to Parquet files and get a lot of benefits here. The main benefit is Azure SQL database might be hundreds or thousands of dollars, but files are pennies to store gigs and terabytes of data. So we store those files in Azure Blob Storage or in Azure Data Lake Storage Gen 2. And if you take a look at the pricing online, you can see that the pricing is very affordable. It is very cheap to store those things. So like we said, we're using Parquet files for staging and Parquet files for ODS. We don't have to. There are other file types available like ORC files, but Parquet is the popular one. It's the one most people are using. You could put CSVs in here too if you want, but you wouldn't want to do a lot of analytics over a CSV if you can avoid it because it can be pretty expensive. Now, that means that your data architecture might look like this, where you're using Azure Data Lake Store for long-term storage. You have pipelines that are feeding into a SQL data mart. That might be where your star schema is. Those pipelines might be written in Azure Data Factory or Synapse or Azure Databricks. So you might write them using SQL, or you might write them using Python, and you might be filling that data, the star schema, into, like I said, an Azure Data Warehouse or Azure SQL database. You might split off alerting. So alerting won't use that data architecture that I just showed you. Instead, you might be feeding interesting events into an event hub, and then from there, you use Stream Analytics to load it directly into Power BI. So by keeping a simple alerting system that only has 1 or 2 or 3 mechanisms, you pull directly from the source into Power BI. So that if there's something like a fraud happening or low inventory or something you really care about, Power BI is getting updated in real time so people can see it immediately. And you can fire all sorts of email alerts and things like that to tell people, hey, something bad is happening. But we're not overloading this for alerting. This is for long-term analytics and for machine learning and things like that.
So in Power BI, you can create real-time streaming dashboards like this. And this is a good example of what you would do if you wanted to deal with alerting. Because as events happen in your organization, we can immediately see a live update in the tiles and line charts in Power BI. So if I were looking to monitor something really bad, like let's say a fraudulent call that got detected, I would want to see that if this number went to triple digits or quadruple digits, I have a big problem that I need to react with quickly. I have a customer that they monitor several APIs on the internet to see if there's a disaster that's happening. And there's always a disaster going on in the world. There's earthquakes or storms or tornadoes or all sorts of things, mudslides, and they monitor these APIs. And if it looks like there's a certain number of disasters happening in the same area, then they report on it. And they built in their organization these really big LED screens on the walls where the dashboards just like this are displaying to keep everybody on the same page so that everybody's monitoring the same thing. And you can build that with Power BI. Now, the way it starts, let me log into my Azure portal. The way it starts is with an IoT hub or something similar to that. It doesn't have to start with an IoT hub, but it can start with something similar. So what I mean by that is, hang on one second, let me just log in real quick. What I mean by that is if we look at this IoT hub that I have, this event hub, right? An application, let's just pretend that whoever's doing the fraud call application is reporting data to the event hub. And inside this event hub that I called IKEH, creatively, right? I secure it. So I basically say, okay, this person has the right to manage send and listen as long as they've got the right key. So when you click on this, you can see, typical connection strings and keys that you use to secure Azure resources. And once that is created, the application starts reporting events that we care about to the hub, and then we have to subscribe to this. Now, in an IoT situation, there'll be flooded messages everywhere. And we're not going to want to subscribe to that flood of messages. And so what we need is something to temper the message load, to kind of soften it, lower it to a cadence that is digestible. For instance, you'll see this, you'll notice that every second this kind of gets updated and we see it. Now, if imagine we had a call center with millions of calls a second and the fraud numbers were pretty high, it would update too frequently. So we couldn't even read these numbers, right? So we need something to kind of lower the speed at which these events are being directed, a governor, if you will. So what we use in Azure to do that is called Stream Analytics. And with Stream Analytics, you define an input. And so here, the input is that event hub. See that event hub? That event hub is the input. And then you specify an output. And in my case, the output is Power BI. See, if I go click on output, and it gives me several different options, and one of those options is a Power BI data set called Stream Data Set. And then you specify a table, and now it immediately starts loading data into a Power BI data set. What data does it load into it? That's based on the query. So if you see the query, what does that look like to you? That's just a regular select statement. So you use this select statement to say, hey, give me all the fraudulent calls within the last 5 minutes, right? So that's what's lowering the cadence of the message load to Power BI. Now, what do you do inside Power BI? Well, if we go into Power BI, and let's say that we create a standard dashboard. This is just a regular dashboard, okay? If I click edit and add a tile, it says, what kind of tile would you like to add to the dashboard? In my case, it's a custom streaming data. And I click here, and it says, would you like to use the stream data set? Where was that stream data set defined? Remember, it was in my output. There's the PBI. If I click on that, you can see I called it stream dataset and dataset name, right? So if I come back here, stream dataset, I click next, and it says, okay, I've noticed that, let's pick a bar chart or a gauge. How about a gauge? What value do you want on the gauge? I want the fraudulent call value. What's the minimum value? If I have minimum in the data set or not, and maximum if I have that, or maybe I can just specify a target, right? That might exist in the data set. But for now, we'll just do fraudulent calls. So I click next, and then we name it, and we'll just say fraud calls gauge. And then we'll click apply. And now you can see that gauge is available to me, and I can like resize it if I'd like to. I can put it up here, right? And now I've added that to my streaming dataset dashboard. And that's it. Notice how we go right from the application source, which is the IoT hub, into the Stream Analytics job, which softens the message load and gives meaning to it. And that's just a select statement. You output it to a Power BI data set, and then you use it in a Power BI dashboard as a streaming real-time tile. And that's it. That's what you do. And you're not overloading your existing data lake with any of the alerting data if you don't want to. Now, if I did want to put it in the data lake, that's just adding another output. So I can output to two things. I can say output to a data lake file so I can do long-term analysis to it, and output to Power BI so I can see immediate telemetry dashboards. That's it. You're well on your way to creating Power BI streaming data sets. Thanks.
Okay. So let's take a look at data virtualization as a concept. So this is a new thing, right? That's relatively new within the last decade. And what this does is it allows us to use files as tables. So what you do is you have data in the file, and then you define a table over it, and you can query the table directly. So we've had data virtualization in Spark and Polybase and Hive and even Power BI for a long time. But let's take a look at what it looks like in Synapse. So I'm going to open up Synapse Workspace here. And you can see that I have some SQL scripts here already built. So for instance, if I want to query Parquet files, you can see here on my screen, look at this, select top 10 from open row set. This is the Parquet file, and I can query it. Give me a couple rows, right? Now you can watch, like I can run this right now and you can see it. See, this is data coming back. So I pulled the Parquet file out, it inferred a schema, and now I can select from it, year, cases, deaths, right? If I don't want an inferred schema, I can create a schema. I can say, hey, go into that Parquet file, the format is Parquet, and the columns are like date, rep, cases, GeoID, right? And look at data types, date, int, varchar. And if I run this query, you can see just those 4 columns, right? And all this data comes back out for me. Now, I can also do some aggregations here, right? So I can say, hey, open up that Parquet file, give me the year and passenger count and a total, and group it. So now I'm starting to do some aggregations and analytics, right? Some basic analytics. And this is all file-based. So it feels like Transact SQL. Transact SQL is operating over those files for us. And we are running just normal queries here. This one's taking a little bit longer, but you get the idea. So we can do all kinds of analytics if we want. We've got an awful lot of power here. This is Transact SQL over files, and it's pretty impressive. Now, another thing that we can do is we can execute over multiple files. So for instance, I can do from, and I can do join, and I can do group by and order by. So I have the ability to join data from multiple files, and those files don't necessarily have to be Parquet. In this case, the file is a CSV, right? So I can run this query, and here's the schema, right? Just like you'd expect. This is schema on read. So in a typical SQL data warehouse, you would define a schema and then load data into it. Here what we're doing is we're loading up a bunch of Parquet files, and then when we use those files, we define the schema. So we're creating the schema on read. Why is that important? Well, in a traditional SQL Server-based data warehouse, let's say that I had a table with 1 billion records in it, and I wanted to add a column to that table. I would have to provide a value to the new column to the 1 billion existing records. And what this has traditionally done is made changes to large data warehouses very difficult. Adding columns can even result in downtime. Maybe you want to make a structural change to the data warehouse. You could be down all weekend making that structural change. And if there's a mistake and you have to roll it back, you could be down and your users might not be able to use the analytics system as a result. But in a file-based analytics system, I can add and remove columns to the files easily, and I can define structure when I'm reading the data using data virtualization. So that means that I can add and remove columns borderline at will without any downtime. Data virtualization typically has this graceful failing notion, which means that if I go to look for a column that isn't actually there in the file, the column just comes back null. It just says, oh, I didn't find that column that you were looking for, so there's nothing there, right? Instead of a failure. That's a lot different than a schema-first relational data store, where if you go looking for a column that isn't there, you error out. That's a hard fail. That doesn't really happen in the same way in using, what we're using here, which is Synapse and using Polybase. Does that all make sense? I hope that makes sense really well. So how do we organize a data lake? We organize a data lake using folders. So we can, for instance, what we used to call staging in a data warehouse, we now call raw or bronze. Or we could still call it staging if we wanted to. There's no rule that says we don't have to use those names. You can use any names you want. But it's probably going to be Parquet files. It's probably going to be a folder. And it's probably going to live in Azure Data Lake storage.
So this is Azure Data Lake Storage. I'm in Azure Synapse. This isn't a course on Azure Synapse, but it gives you a good idea of what Azure Synapse is. And just to kind of let you know, what you can do in Azure Synapse is you can collect data from a lot of different places, like this is SQL data, or you can link data. If I click here and I say, hey, what external data can I link to? I can link to a Cosmos DB or to Azure Data Lake Store. We've been talking mostly about Azure Data Lake Store, but Cosmos can work also. And when I go in here, you can see I've got a storage account for ADLS, and you can see that this is the base folder structure. You see the bronze raw right here. And I just wanted to give you an example of bronze, what that folder structure looks like. Now, one of the great things about Azure Data Lake Store is it's just like HDFS. So anything that works with HDFS and Hadoop and Spark can work with Azure Data Lake Store because the front-end API is the same. So here Synapse is connecting to ADLS and it sees a bronze raw folder, and we have subfolders just like HDFS. And what we do is we organize our subfolders by the source that's coming in. So for instance, if I had Great Plains data or SAP data or CRM data, that data would get its own folder. And then usually underneath there, we have the date we brought the data in. So for instance, maybe I've only been running this for 2 years so that I have 2019 and 2020 data. And then maybe I only pull the data once a month. So let's just pretend for the CRM data, I have a month end load, and I take that month end load and it drops it as JSON, which isn't great for analytics, but it's good for raw. We can turn that JSON into Parquet later if we'd like. But you can see that, I've run this through July, August, July or so, and I have a file for each month. Now, in a normal transactional data warehouse, like a SQL Server data warehouse, a relational one, um, you would load the data into one table. The reason why we don't need to do that in a file-based system is because the data virtualization will work over all the files in a folder. So if I wanted to create a table, a metadata table called raw, so CRM raw, right? I would point it to this folder and it would ingest all the files underneath it as one virtual table. So I could say select star from CRM raw, and all the folders and files, it would infer a schema, or you could create a schema over all those files with all the right columns and data types. That would all work. All right, there you go. I just wanted to give you an example of what a data lake store would look like, and particularly in Synapse, because I think the tool is pretty cool and it consolidates a lot for us all in one place.
Um, we the ODS, we can call it ODS, or we call it clean, or we call it prepped, but most commonly it's called silver. So we went from bronze, which was the staging area, to silver, which is our ODS. And that is where data has been kind of clean, just like the ODS data was clean before. And it is where data can be joined, but the star schema does not exist there, right? So the question is, where do we put the star schema? Well, we can put the star schema file-based. If we do that, we would call that folder gold, or we can call it a data mart if we want. Or we can put it in our relational database, like our Microsoft SQL Server. Or we can use a Power BI dataset. We can use Power BI to pull in tables and then clean them up using Power Query, simplify them so that there's only 5 or 6 tables, and we can design the star schema in Power BI if we want. That is not my favorite thing to do. What I prefer to do is build star schemas in Azure SQL Database. That's my preference. And so I hope you would strive to do that too. The reason why I like star schemas in an Azure SQL Database is I like to use those star schemas in Excel or Power BI or other places. SQL is fast when you have column store indexing over star schemas. It's very, very fast. And the refreshes are fast. So we can, as engineers, avoid building the star schemas using Power Query because it slows down the data refreshes pretty significantly. And it relies on cleaning that up in the data extraction and in query folding, which can be fast, but it can be also very difficult to maintain and difficult to troubleshoot and difficult, sometimes just so slow that we lose our ability to make it faster. So we'd prefer to organize the ODS in the silver area using Parquet files, and then using our data pipelines to build a data mart in SQL Server, and then from there do just a straight simple extraction into Power BI, very simple and clean, so that the star schema exists in Power BI.
So this is a good example of a star schema in SQL Server. So this is the sample, and you can play around with the sample. This is AdventureWorks DW, and here you can see that we have a bunch of fact tables, and we can see that we have some dimension tables, just like we talked about earlier. Now, in the silver, which I haven't shown you, in the ODS portion of the data lake, that is typically going to be Parquet files. And so you are going to have hundreds of folders and files in the silver area because you're going to take data that's interesting to you. You're going to put it in Parquet so it's compressed, and you're going to leave it there pretty much as you found it without a lot of modifications so that you can tie it back to the way the raw came in as JSON. You're going to put it in Parquet and Silver because when we run analytics on it, it's much, much faster than running analytics on the raw JSON, right? Then from there, you're going to put the star schema in SQL, just like this. And this is going to be quite a bit different than what you saw in Silver. So with where Silver will have 300 tables, here you're only seeing about 20 tables. And that's pretty typical for a star schema in Azure SQL Database. One final note, I would make the SQL version that you use Azure SQL Database Hyperscale. We have found that when we load using Spark or using Synapse, that when we load data into SQL, we get a lot of log contention and it slows everything down. And the reason why we're getting a lot of contention is because remember, our data pipelines in a data lake are typically in parallel. We have multiple nodes creating pipelines at the same time. And if they all hit the same SQL database, they overload it and the log can't keep up and it gets really, really slow. But if we use hyperscale, the log can keep up and we can load data very, very rapidly, terabytes in minutes. I mean, really, really fast. So like I said, use Azure SQL Database Hyperscale, put the star schema here, and I think you'll find a lot of value there.
Now, what do we do with the math? The sums, the averages, the things like that? Well, we can create aggregation files that are Parquet files that might be stored in an aggregation folder in the data lake, in Azure Data Lake Storage. Or we can create tables that are aggregation. So this would be like sales by year, sales by month, sales by day, can exist in the data mart in SQL Server if you'd like. Or you can build DAX in Power BI that does those measures and calculations for you. Of these three options, I prefer doing it in DAX. I think that DAX is very fast for creating aggregations. I think the problem with building aggregation files or tables is that they just are always out of sync with each other. So let's say that you have an aggregation table called sales by month and a different one called sales by year, and you want to change how you do those calculations. My experience is when you build aggregation files and tables, the month and year things are often out of sync, they're often wrong, they often are inconsistent, and they need to be troubleshot all the time, and it's very, very difficult to keep them maintained. Where if you keep the star schema in the data mart and you extract it into Power BI and you build the DAX in Power BI, now the DAX, the slicing and dicing is done in the DAX, right? So the monthly and yearly aggregations are just automatically done for you in the DAX, right? Using the filter context. You don't need to maintain it. They're always consistent with each other. And it's much, much easier to have clean and accurate calculations in DAX than it is hand building it yourself using Python or SQL or something like that, right? That's my opinion. Other data engineers would have other opinions on that, but that's how I prefer to maintain it.
So in Power BI, I bring the star schema in. Notice that these tables are coming in raw with dimensions here and a fact here, just like you just saw in Azure SQL Database Hyperscale, right? And if I come in here and I edit the queries, And what you'll see is that here's the table, and I'm not really massaging anything in Power Query that much. Now I will, in the real world, I will do a little bit. Like I'll combine some columns and I'll remove columns I didn't want, and I might do some light editing here, paying attention that I'm always using query folding. So query folding, remember, is our ability to right click here and say view native query so that we can see it here. We don't ever want to do so much in Power Query that we get out of query folding because we start really losing performance when we do that. I've got another video on my channel that talks more in detail about that if you'd like to see it. Okay, so what I do is I usually create a table called measures. And the way I do that, just in case you're curious about how to create a table, is you just come in here and click new table. And so I create a brand new table called measures. And then inside here, I create a new measure. And this measure is just really simple. It's just DAX that says count rows. Now, what I was talking about counting rows is notice that in this visual, I'm counting rows by month, right? And you can see that as the months progress, I can see my total count here. But I can also use the exact same DAX, and instead I can do it by year, right? I can say here's calendar year and give me total sales, right? And now you can see my calendar year, here's my total sales. Let's see. Oh, hang on. Um, let's total sales. I want to add the calendar year there. There we go. Okay. So you can see by year, here's the sales that are happening, right? Now, when I talked about aggregate tables not tying up, the totals here and the totals here wouldn't tie up easily in an aggregate table. It always requires maintenance. But what I want you to notice here is my visual here uses total sales event, right? And my visual here uses total sales events, right? So it's the same DAX, this DAX here, that is just giving me the total number of rows by that year or month. Power BI does that consistent technology, that consistent mechanism for you using the evaluation context. I've got a lot of DAX videos if you want to read more about this, but for this purpose, DAX is providing us a lot of power and it's very, very fast for us. So when, for instance, when I highlight one of here, I get on the fly, I get the visuals being updated. That DAX is getting reinterpreted on the fly. Very, very powerful. So I try to keep my aggregations in DAX to kind of tap into this power and speed. Thanks.
We have other uses of folders here too. For instance, snapshotting. Now remember, if we have file-based data stores, it becomes very easy to snapshot data. So for instance, in our financial system, if somebody says, hey, I want to know what the financial system looked like in August 2019, it's just a copy. We just copy that data over to other files, and now you can examine that data all you want. If a data scientist says, I want a quick snapshot view of some data, copy it, give the data scientist access to it in the data lake, and they're done. Why can we do that? Well, in a SQL-based data warehouse, copying data is very expensive. It takes a lot of money. So if you have a 50 terabyte ODS and somebody wants a copy of that, because SQL is expensive to license and maintain, and the backup and restore takes so long of that 50 terabytes, you avoid doing that. You don't like snapshotting things like that. It's expensive and time consuming, and nobody wants to keep it around a long time. But when you move to a file-based system, now these things are cheap to do. You can easily make a copy of terabytes of data, pay a couple $100 a month to maintain it, and that data scientist can go to town on that data, just completely shred it and rip it apart and analyze it and put data virtualization tables over it, maybe create their own star schema over it, do whatever they want with it, and the minute they're finished with it, it's just a delete, right? In a data warehouse, when you want to delete 1 billion records because of the logging and the MDFs and all those things, when you delete, that could result in downtime. But in a data lake, deleting is just a file delete. Nobody cares about it. So you can really start to see the power of moving some of these analytics systems off of a relational store and moving into a file-based Parquet store with data virtualization. It is very, very powerful and affordable for you to do that. We can do it for temporal tables and for archiving. You know that 10 years of data warehouse that we were concerned about? Take 9 years, put it in a file-based data archive, call it a day, and now you've got a lean and mean 14-month data mart where you're doing really good data analytics that are up to date and current, And the beauty of this is this. If you have bronze, silver, gold, archive, snapshot, and you do data virtualization, meaning you define tables over those files, and you've got other data that's highly structured in a data mart, what that means is in a single join, in a single query, you can pull data from all those different places. And in Power BI, you can pull data in from all those different places. And in Python and SQL, you can pull all those things in from all those different places. So if we go back to our demo, right, if I want to, for instance, let's say I want to do archiving. So what I do is I create a file that is a Parquet file. And then I specify the data source of that file is a specific location. And then I create a table. Look at this create table structure. You know this. But instead of defining the columns, I say this file that I've built a connection to in my data lake needs data hydrated from this table in the data mart. It's just a select statement. So using this method, I can take a whole bunch of data from the data mart and I can load it into a file and then delete it from my data mart, keeping my data mart lean, mean, and clean, and having the file still there as being used, just like this, right? So I can query it, just using open row set, or I can define a table over the file. That external table exists in my metadata repository, and I can query that table directly, right? What does that mean? That means that as I move data from the expensive SQL Server over to the cheaper files, I don't lose access to it, and my queries don't necessarily need to change. So if I've got a report that's looking at older data, those queries can stay the same, and I could be moving data into FileBase underneath it without the reports ever changing or being modified. There's an awful lot of power in building a modern data lake like that, and Synapse gives us the ability to join that data from SQL or from files in a seamless manner, and Power BI can use it, machine learning and deep learning can use it, data scientists can use it, your auditing requirements that you keep data around for 10 years or whatever is all being met, and the fundamental code is not really changing that much. So in conclusion, yes, we still make star schemas. Yes, we use slowly changing dimensions. Yes, we can still use cubes if we want. But don't be afraid of files. Don't be afraid of building Parquet files and putting data virtualized table structures over it. We can still use SQL. You love SQL, I love SQL. We can still use SQL. We can still build SQL data marts. Try to keep our aggregations in Power BI. And if you do that, you're going to create a really good analytics solution for your organizations. Now, I realize I have a 50-minute session, and so I've purposely kept my video short so that we can stop and start while we talk live, and we can use the remaining of the time for a Q&A and for discussion. I can show you other things if you'd like, but thanks a lot and have a great day.